So now that we know the equations for Kepler, we are going to use them with our sample problems so you can do your practice problems on your own. Now, remember the main equation we're using is t squared equals kr cubed. So you need to know on your calculator where your square button is, your cube button, your square root, and your cube root. So hopefully you figured that out. If you don't, you should talk to one of your teachers to help you with that. All right, so our first problem is a planet in our solar system has an orbital radius of 50 AU. What is its orbital period? Okay, so we see a couple things to give us hints of what this first thing is giving us. So we see radius, and we see 5 AU, and we also see that we have here that it's in our solar system. So because it's in our solar system, we know that K is equal to 1. That's not true if it's not in our solar system, but it is. So in my given, we're going to have R is equal to 50 AU. And we also see, oops, that's a U, right? And then we also see that K is equal to 1 year squared per AU cubed. And we're trying to find its orbital period, right? Period is not P, right? Period, it seems like it should be P. But period is not P. Period is capital T. So T equals question mark. And the new equation that we got is T squared equals K R cubed. So just like in the activity you did, we need to solve for T. There the K was 1. It's 1 here as well. So we could cross it off, but we'll leave it in just so you can see how it works. And we need to get rid of the square. So to get rid of the square, we're going to take the square root on both sides. So that will cancel out this and that. And so then we're left with T is equal to the square root of K R cubed. So then when we calculate it, T is equal to the square root of 1 year squared over AU cubed, that's a whole parentheses, times 50 AUs cubed. So check units to make sure everything matches and you didn't mess anything up. So you can see the AU cubed cancel out with the AU cubed, and the square is going to cancel out with the square there. So that's good. So we're going to end up with 50 cubed. So I go over to my calculator and I do 50 and I raise it to the third power. And that tells me that it's 125,000, but I don't want 125,000. So I'm going to do the square root of my answer, and that gives me 353. So that means that my period is 353. What are the units that are left? Years. All right, because it's period. So 353 years and some odd amounts, right? But we're just like we are a little more than 365 days. We still call it 365. Does that make sense? So we go back with the activity, and we see that the radius of this planet was 50 Earth orbits away. So it makes sense that it's going to take a lot longer for it to get around than the Earth does. So good. It's passed the sanity check. We can go on to the next problem. So problem number 2 says that a planet has an orbital period, so here we have orbital period of 5 years. What is its radius? We're still in our solar system because K is still equal to 1. Awesome. So we do given, and we say T is equal to 5 years. And we say K is equal to 1 year squared over AU cubed. This is the easy part, right? We're trying to find the radius. It's the same equation. So T squared equals K R cubed. But now it gets hard. I got to solve for R. Okay, what am I going to do? Well, I can't do anything about the cube until I get rid of the K. So let's get rid of the K. So we're going to divide both sides by K. That'll get rid of the K. And then I got to get rid of the cube. To get rid of the cube, the opposite of cubing is a cube root. Weird looking thing, but you should have it somewhere on your calculator. You can also raise it to the 1/3 power, but that gets rid of the cubes, right? So we end up with, in our solved step, that this is the only thing left, right? R is equal to the cube root of t squared over k. So now we can calculate it. R is equal to the cube root of t squared, which is 5 years squared, all over 1 year squared per AU cubed. That's all under the parentheses. So I'm going to check my units because otherwise I'm not even going to go any further. And I see year squared cancel with year squared. The AU comes on top because it's on the bottom. The cube goes away because of the cube root. Yay, it's going to come out AUs. And so it's basically going to be the square root of 25, right? Because 5 times 5 is 25. And then you take the cube root. Sorry, I said square root. Wait, we get the same answer back, right? Not the square root, the cube root. It's not the same thing. So it's going to be 25. And depending on your calculator, you might have to put the cube in, or you can raise it to the 1/3. So I have to put 3 and then use the cube root button. And then 25. And that comes out to be 2.9. So 2.9 AUs, right? Because that's what I had left, right? I had just this AU left. And I say, does that make sense? Well, 5 years is 5 times further away than or 5 times as long as the Earth takes to go around. So it would make sense that it would be a little bit further out, right? Because it's t squared r cubed. Not directly related, but they're close, right? So always do that check. Does it make sense? Yeah, that makes sense. We knew it was going to be more than 1. All right, last one. So here's a little more difficult problem we are going to be looking at. It says satellite A has an orbital period of 25 days and an orbital radius of 20 kilometers. What is the orbital period of satellite B if it has an orbital radius of 15 kilometers around the same planet? So notice this isn't in our solar system, so we're going to use the ratio method for this one. So in my given, we know that TA is 25 days, and RA is 20 kilometers. So that's satellite 1. Satellite 2, satellite B, we know its radius, right? So RB equals 15 kilometers, but we're trying to find the period of satellite B because we don't know what it is. Now we know it's going to be less, right? Because we can see that we went from 20 kilometers, right? We went from 20 kilometers here to 15 kilometers there. But we don't know exactly what it is. But we just know it's less. So it's going to be something less than 25 days. So for my equation, we're going to set up a ratio. So remember, our ratio is t squared over r cubed is always equal to t squared over r cubed. And then I'm just going to put a's on this side and b's on this side. All right, so now we need to solve for TB, right? I need to solve for TB without the square there. So the first thing I'm going to do is I'm going to multiply both sides by RB cubed. RB cubed, right? Because that'll get rid of this RB cubed, and that'll get rid of this RB cubed. That doesn't look much like a B, does it? There, looks a little more like a B. And then I need to get rid of the square. So to get rid of the square, I'm going to take the square root. So square root, and that gets rid of the square and gets rid of that square, right? Oh, what a mess. Let's see what we've got. So in my solve step, I've got t, because that was all that was left, is equal right here, right? Here's my t. Remember, my t is right there. It's hiding, but it's there. So t is equal to the square root of rb cubed, because remember, we multiply by that, and then the ratio we had left. So ta squared over ra cubed. Whew. All right, we're almost there. So calculate t is equal to, we got to make sure you plug in all the right numbers. So RB was 15, so 15 kilometers, and it's cubed. times TA squared. TA was 25 days, so 25 days squared, divided by RA, which is 20 kilometers. So 20 kilometers cubed. This is a kilometers, right? Okay, so let's check our units so we don't go too far and then we know we messed up. So we can see kilometers cubed cancels out with kilometers cubed. Yay. And the square is going to cancel out right there, so I'm going to end up with days, and that's awesome because that's what I needed to end up with. Let's move this up a little bit. And so now let's plug everything in. So it's going to be equal to, so let's do the top first. So it's 15 raised to the third power times 25 squared. So that's going to give us this huge number on top, which is, well, that's a weird looking squared root. Let's see if we can make that look like more like a square root. I don't know what happened there. Make it look more like a square root. So square root, that looks better. 2109375 days squared, because we know it's going to cancel, we just haven't yet. And on the bottom we have 20 raised to the third, so that's 8,000. So over 8,000. There's no unit left there anymore, right? So we take the 2109375, we divide it by 8,000, and then we take the square root of the answer, and we get 16.2 days, which again makes sense because we go back and we look up here and say, oh, it was, whoops, not that one, it was this one, woo, right over there, was how many days it was. It was 25 days. We said it was going to be less than 25. We said it probably wasn't going to just go down by 5 because the radius went down by 5. So it went down just a little bit, so that makes sense. All right, there's your last problem.